So I'm going to start drawing force vectors into this thing and just sort of see what happens. The friction force depends on the normal force, so I've got to do a vertical analysis here. We go, okay, gravity's pulling down with a magnitude of mg. That's 117.6 newtons. And there are no other forces tampering with the vertical direction here. And I'm on a perfectly level surface, so this is one case where the normal force is just equal to mg. That would be 117.6 newtons. And having a force vector represented this way has always bothered me because I like to attach the tails of the vectors to the object that I'm studying, so I'm going to put it over here. This is the applied force. And for the first problem, that's equal to 40 newtons. Just kind of scribble that out. And then I have a static friction force fighting in the direction that opposes the slipping that is trying to happen here. So we're going to use a lowercase f s for that. All right, so first I want to address the most common mistake with this problem, which is to assume that the static friction force is maximized. So the formula for static friction is like that. Let's see, I wanted to switch to, yeah. It's supposed to be yellow, but that's okay. And if I computed that, I would get, I have a static friction force of 0.5, so I get 0.5 times 117.6. And that would give me 58.8 newtons. All right, so the most common mistake for this problem is for students to just say, okay, static friction is mu times n, I get 58.8 newtons. But you have to ask yourself whether or not that makes sense. You're pushing with 40 newtons to the right, and the friction force pushes with 58.8 newtons to the left. That means the box would suddenly start going the opposite direction of the way that you were pushing. It doesn't make sense. So we found a maximum static friction force. If you push on it with a force that's less than that, what static friction does is just hold the object in place. So if you push on the box with 1 newton of force to the right, the static friction is 1 newton to the left. If you do 10 to the right, it's 10 to the left, and so on all the way until you get to this maximum value, which is actually the answer to part B. So I don't know, I'll just move this over here and say that now that I know the maximum value is 58.8, I know it doesn't break loose when I push on it with 40 newtons. So the static friction force must be 40 newtons in magnitude in order to hold the box in place. Then I could get just a little more formal about the breakaway force calculation. And the assumption there is that I'm right at the cut point where the static friction force is maxed out. All right, so we do a lot of stuff with static friction where it's maxed out. We're right at the breakaway point where things start to slip, just because that's the interesting question to ask about static friction. All right, if the static friction force is maxed out, then I'm talking about FB, the breakaway force. So the breakaway force, just kill that real quick, trying to get better about color coding. So the breakaway force is equal to Fs max, which is mu s times the normal force, which is 0.5 times 117.6, which is 58.8 newtons. All right, so I threw this in here as a way of illustrating by example that static friction forces are variable. If you don't push very hard, The static friction doesn't have to push very hard to keep something held in place. And the harder you push, the bigger the static friction gets. Eventually you hit a breaking point where the object is going to break loose and start sliding.